Ionization energy is the energy in joules needed to strip a mole of electrons away from a mole of atoms. This is going to be very important to our understanding of the structure of the periodic table. So how do we measure ionization energy? Well, one method for measuring the ionization energy is to put a gas into a tube with electrodes in it and put a voltage across the tubes and slowly increase the voltage until we see the gas conducting electricity and emitting light. And the voltage at which that occurs can be used to calculate the ionization energy. However, most high school labs don't have the equipment to do that, and many do not have the correct tubes. We do something like that soon, however. Now, we do know how to react metals with water and stronger acids, however. And so if you would perhaps look at a video of sodium reacting with water, you'll see that sodium reacts with water very vigorously and without adding any additional energy. It reacts with cold water. This reaction oxidizes, that is, pulls electrons away from the sodium. We say oxidation occurs when metals lose electrons. So the sodium ions then are ionized. The atoms are ionized to sodium ions in the reaction. The more intense this reaction is then, the lower is the energy needed to strip the electron away and give it to the hydrogen atoms to turn into hydrogen gas. When we react potassium with water, it seems that these large potassium atoms, significantly bigger than sodium, reacted a lot more vigorously than sodium did, so it was easier to get their electrons away and give them to the hydrogen. And what would you predict the reactions of the largest alkali atoms, rubidium and cesium, to be like? You can switch to a YouTube video that shows the reaction of rubidium and cesium and see if your prediction is correct. So we see as the size of the atom increases, the intensity of the reaction increases. The water has enough energy to cause all of these metals to lose their electrons and give them to the water to make hydrogen gas. And sodium hydroxide or potassium hydroxide are also produced. So as the size of the atom increases, the energy needed to pull the electrons away, the ionization energy, must be decreasing, as we can see as we go from sodium to potassium to rubidium to cesium. The measured ionization goes down from almost 500 to less than 380. Measurements, therefore, confirm our understanding from the reactions with water. Now you can continue the study of relative ionization energies by exposing less reactive metals than alkalis to water. Calcium, however, is one of the few metals outside the alkalis that reacts at all, even with hot water. The hydrogen ions in the water are too dilute to take an adequate quantity the electrons away from the less active metals. So you can do an experiment now, and the experiment then uses acids that are a little stronger than water. More hydrogen ions are available in vinegar, for instance. This is a weak acid, and in hydrochloric acid, which is a strong acid. And we would encourage you to do this experiment with metals such as magnesium, calcium, tin, zinc, and aluminum. Remember, when you're doing such a laboratory, to wear the proper protective gear, because these acids are dangerous, especially to your eyes, but even to your skin and clothing. So be very careful when you do this.